Okay, so I'm just gonna really quickly finish off where we left off yesterday or on Monday. So the last sort of transportation fuel technology that we haven't covered, hydrogen fuel cell vehicles. So this is still an electric vehicle because it uses electricity to directly power the drivetrain. Okay, except the electricity isn't coming from a battery, it's coming from a fuel cell stack, which is undergoing a specific chemical reaction to basically produce the electricity. There is like a battery pack in here that allows it to still do things like regenerative braking to get some of the efficiency benefits of being able to sort of backstore the energy, but the drivetrain is almost exclusively going to be powered by the hydrogen itself, by the fuel cell. So this is pretty similar to an electric vehicle, except instead of like a really large battery, you've got your fuel tank, which stores the hydrogen. And those things can actually store quite a bit of hydrogen at a pretty high pressure. And then you have your fuel cell stack here, which converts hydrogen by undergoing a chemical reaction with oxygen to produce water, which is an exothermic reaction. And we'll see how that mechanism actually happens in just a second. Yeah.
How does the battery of BEV compared to a fuel cell?
I mean, they're going to be like the same batteries in the sense that like the chemistry is going to be, within the subset of chemistries that are used in a full battery electric vehicle. The main difference is just that it's a lot smaller,
yeah,
right?
That's exactly what I meant.
Yeah.
In the sense of sustainability and critical minerals, like the ratio of how much of them you use for either battery.
Yeah, well, so the battery is, yeah. So naturally the battery is smaller. So all of the production side environmental issues with producing the battery and all the like material flows, those are all going to be like smaller. But right, the bigger question when we're thinking about holistically the picture of sustainability of this type of technology is the production of hydrogen. And so currently, where's my, yeah, so there are a couple different ways that hydrogen can be produced. Most of the hydrogen today that's being used in like industrial purposes, that's mainly produced through something called steam reformation, which is from natural gas. So this process is not a, we'll say, super clean way to produce hydrogen. You can also do the exact reverse reaction that's happening in the fuel cell, where you are taking water and separating it into hydrogen and oxygen. And this is a process known as electrolysis. And so you can split water and then isolate the hydrogen to use as a fuel. But of course, this takes the same amount of energy to make the hydrogen as you get out of the hydrogen. When we're thinking about it from a, like a chemistry perspective, from a practical perspective, you are, of course, losing energy because there's efficiency losses in doing this process, going this way, and then when you go the reverse way, you also get losses. So yeah, that's one of the sort of bigger drawbacks, I would say, of doing this hydrogen production. So really this is, you can almost think of hydrogen in this sense as a form of storage in an analogous way that batteries, right, are storing energy that has already been produced. We're putting electricity in here to make the hydrogen in order to get it back out sort of later on when you're actually using it in the vehicle.
Is US or nationwide, or are they
this one is US. I don't actually know what the picture looks like internationally. Yeah, and it's a little outdated, but these are fairly sort of like low volumes when you think about the actual quantity of hydrogen that would be needed if you wanted to do, if you're thinking about like a large scale transition to something like hydrogen fuel cells. Yes. Yes, yeah. Yeah, I mean, these are all chemical processes. So this is not combustion of any sort, right? Because there's no, that would be combining with oxygen. So this is essentially the reaction that's happening to extract hydrogen. And if you look at the sort of byproducts, carbon monoxide and carbon dioxide are both sort of common byproducts of this type of reaction. I don't actually know. Yeah. No. Yeah. Well, the conditions in which the reaction happens like requires a lot of energy input. So you're not getting the exact same type of loss of like heat in the sense that like in the combustion process you can't capture all that heat, but there's a lot that has to go into it to begin with, right? Okay, so fuel cell, the way this works is the exact opposite process of electrolysis. You're combining hydrogen and oxygen to produce water. And in fact, when you think about this process happening in a car, right, when we're talking about the combustion of fossil fuels, right, that leads to all those combustion byproducts getting emitted out of the tailpipe. For a hydrogen car, you press this little button and it squirts water out when you feel like releasing it, right? And so the only byproduct is water. So it's actually a large amount of energy in this exothermic process, and which is why that you get enough sort of energy density to do something like moving a car. You have this sort of proton exchange membrane here. It's a catalyst that facilitates the reaction. It reduces the activation energy needed to essentially undergo this exothermic reaction. And just to give a sense of modern day fuel cells, you are getting about 300 miles with a 5 kilogram hydrogen tank. The economics of it isn't great right now. So it costs anywhere between, let's say, $12 to $15 for a kilogram of hydrogen. And that's actually, if you think about it in terms of cost of gasoline basis, you're actually similar, right? It'd be above like $10 a gallon. So unlike electricity, hydrogen fuel cell vehicles cost a lot more to refuel. And in fact, if you were to go out right now and you lease a Toyota Mirai, Toyota will hand you a credit card that has like $15,000 on it over the course of your lease, where you get to fuel for free as an incentive for using their hydrogen vehicle. There are no used Mirais because yeah, there are no used one. Well, I'm not going to say there aren't any, but hydrogen vehicles are only leased by automakers. You cannot buy them, so they don't go back out on the secondary market. Oh, you just bought one? Oh.
I don't know, like it's a 2019 Nexo.
But I thought that they don't let you buy. I thought it was only on lease. Is that not true? Okay, well, apparently not. So you have a hydrogen vehicle. So tell us your opinions about.
No, I was thinking about it. I do the fuel economy and like, I don't know, it's like 300 more per month than gasoline right now.
Yeah, to pay for like operation. Yeah, for sure.
Amazing and no pollution.
Yes.
Nice.
Does Hyundai give you a fuel card?
So this is yeah.
They do.
And that's why I was asking. For new ones, yes.
Okay.
Like 69,000 for new ones.
Okay.
Used ones don't give you. That's why I was asking if there's any incentive.
Not that I know of, because I didn't even know that you could buy them used, apparently. So yeah, so for this my information is probably outdated, but for a long period of time, essentially what the automakers are doing is they buy back all of the leases, so that they can essentially take them back and do analysis on them. So there's like a big graveyard of Toyota Mirais out in Michigan, actually, but apparently they're selling them used now, so that's changing. Yes. Fast. It's like a gas station, right? You just go in there. Depends. There's actually, I've heard that it's fairly variable depending on the station itself. I know that like you're not supposed to go over like 10,000 psi or something, but the station in Westsac was broken for a while, and so you'd fill up and the needle would go past, but it would keep going, and like yeah. Actually, from a safety perspective, it's been a common thing to sort of worry about, right? Hydrogen is like one of the most flammable gases, and doubly dangerous because that combustion is colorless, so you actually don't see the flame when it's burning. But actually, my understanding is that these things are fairly safe. They operate in very high pressure, so if the fuel tank does rupture, the gas escapes very quickly, as opposed to like gasoline, which just pools there, right? So yeah, I mean, there certainly are safety concerns. Anything you're operating with at high pressure is going to be scary, but yeah, I think it's safer than most people would think. Okay. Last little bit, environmental impacts. So with oil, there are sort of natural effects associated with drilling and production, right? So disturbing local ecosystems, but there are lots of sort of technologies that are trying to help decrease like the immediate footprint, and help with the efficiency of like exploration activities. Yeah, so list of variety of technologies to help with that, but there are sort of inevitably some kind of disturbances to your ecosystem. Hydraulic fracturing, so this thing that was developed that really came to the forefront of the last like decade and a half, uses a very large amount of water. That was one of the big issues with this sort of technique, in order to extract the fuel out of the fractured rock. So there's issues with how the water may affect the sort of geological formation in the process itself, and then afterwards, how you deal with the fluids. It produces the fluids that come out of the hydraulic fracturing process contains all sorts of crazy chemicals. And so, there are issues with figuring out how to properly treat it before disposing it, or if you're just going to store it somewhere, making sure it doesn't like leak or spill, especially into groundwater tables. There's this famous town in Pennsylvania that had these issues where you could actually have like flammable water coming out out of your sinks, right? Because of leaks into the groundwater table. And then the other one related, the other big one related to oil spills, right? And so a lot of these accidents happen in the transport of oil, moving them from well to refineries to other parts of that distribution system, cause all sorts of bad things. We've come a long way in developing regulation and industry standards to help reduce the frequency of spills and also the way that we respond and clean up these accidents. There's been a number of fairly big ones, right? And so you can see the sort of relative size of some of these spills. It's pretty interesting. If you look at the sort of magnitude of this chart, so one thing that always sort of struck me, if you guys all remember the Deepwater Horizon coverage on the news, and you can see those like the underwater cameras of like oil kind of just going into the ocean. And that was over a period of a couple months, right? And so if you think about that quantity of oil, actually, we as a society, we send more than that amount that spilled, that entirety over those couple months, we send that amount into the air every day, right? So one thing to keep in mind. Yeah, you can see the relative size of the deep water oil spill compared to our daily oil consumption. Okay. Any questions about any of this? Okay, so we'll move on. Yes.
It's not about environmental oil, but about natural gas. So we see these big natural gas leaks on the news. Would flaring of those make sense from an environmental perspective?
Yeah, so when we talk about emissions of or emissions in general, right? We can categorize these into two types of things, right? You've got greenhouse gas emissions, which are things that affect climate change, and then you have local air pollution, which are local pollutants that affect air quality and corresponding health of like local populations. So methane is a really bad greenhouse gas, right? So it is, what are we at now? 30, 32? Yeah, so 28 was the old number, and I think it's back down. Okay, well, all right. Anyways, about 30 times worse than CO2. So what that means is that the effect on like radiative forcing is equivalent to, 1 part of CH4 methane is equivalent to like 30 parts CO2. So really bad from a greenhouse gas perspective. And so flaring, right, would essentially convert your methane into CO2. You are just combusting it as it comes out. So that's good from a greenhouse gas perspective, but then it can be bad from the perspective of like local air pollution. So, you pick your poison in some cases. Yeah. Well, so yeah, from an economic perspective, you would want to take advantage of that fuel, right? And so it's not always possible, but to the extent that they can, trying to capture that and use it as a fuel is preferable. At least then you can get something beneficial out of it. Yeah. Okay. So good segue. So we've talked a lot about the sort of technical aspects of how a lot of these technologies work, right? But just because theoretically it's possible to have like nuclear fusion doesn't necessitate its success as like an energy source in the future, right? So a lot of where we are and where we're going is sort of driven by the economics and costs associated with a lot of these energy technologies, and then broader plays a big role in how our energy system sort of operates. So from an environmental perspective, we focus on things that are like clean, right, and green alternatives and sustainability. But today we're going to really sort of dive in and cover concepts that pertain to how some of these things come about in sort of a economic or financial sense. So we're going to talk about concepts of like discounting, NPV, cash flow, and all of this. And so the types of questions that we want to be able to answer, right? Generic things. So wind turbine operates for 10 years. What's the cost of the electricity that it produces? If you're thinking even on a personal level, like figuring out, does it make economic sense to install, solar PV or a solar water heater on your house? Like, how would you go about making those calculations? It can be at a larger scale too, right? If a company wants to make investments in like energy conservation, what's the value of the energy savings that it would be making? How long would it take to repay that upfront investments? How you might compare the cost of owning and operating an electric versus gasoline car, right? And so we already heard an example today of someone who's done at least some calculations, right, to think about these things, right? And so a lot of the green or sustainability values that we think about and that we value, how might we include that, as a cost in this sort of calculus? Okay. Nomenclature, first off, cost versus price. I know as someone mentioned, there's some econ people here, right? So cost, important concept to sort of distinguish. So cost is essentially, in this context, the amount of money we sort of sell the energy for to make a desired sort of rate of return or profit on our investment. It's really thinking about how much money it is required to sort of produce that energy, right? And then once you have that figure, you have an understanding of sort of these concepts. Price is essentially what people pay, right? And so this is determined by market forces, and oftentimes we interchange the two, thinking about price and cost as sort of the same thing, but that's not always going to be the case. Okay, so first up, interest rates versus inflation rates versus discount rates. So these are sort of closely related concepts, but they are not the same. And we're going to try and sort of dive in to think exactly what each of these mean and how they play a role in the way we think about money and how that translates to like funding projects, for example. Okay, so interest rates, cost of borrowing money. Someone comes up to me, says, hey, Alan, can I borrow $100? And I'll say, sure. Here's $100, but pay me back, $105, next week, right? And so that is the cost associated with borrowing money, right? And I wouldn't do that. I have a much higher interest rate. No, just kidding. Inflation rates. So this is a decrease in purchasing power over time. You guys, we're all kind of experiencing this in sort of the overall market right now, right? The inflation has probably been faster or higher at this point than any time in the sort of recent past. And then discount rates, which will be a key piece of a lot of the economic analysis that we're going to be doing in this class. And it's related to both of these things, and that it sort of informs what a discount rate should look like. But more generically, it's the time value of money. And so we'll get a little bit more specific with that in just a bit. So let's go through these one at a time. So inflation. So this is related, again, to the increase in the cost of a good or service over time and decrease in purchasing power. When we sort of model it, it's modeled in a very similar way to interest rate. So under inflation, a future amount of money doesn't have the same purchasing power as if there hadn't been any inflation. So any examples of this that you guys can think of goods or services that have been experiencing inflation? Bikes? Yeah. It's actually a little bit tricky to talk about right now, because there are things associated with like supply and demand that are like shifting prices as well, right? And this is not always directly sort of related to that, but yes. So like if you were to try and buy a bike, for example, and you could go back in time like 5 years, it'll probably be more expensive today, and some of that is going to be due to inflation. Okay, and so you can calculate the value of future money if you have an understanding of the inflation rate. So in this example, let's say $100 in 1975 is worth $426 today. You can calculate small f here, which would be your inflation rate, by plugging in. So F0 would be your starting value, $100. F would be 426. And then N is the number of years between then and now. So what would that be? 48. So your N would be 48, and then you can solve for little f, right? And that would give you your inflation. So the way that's that inflation generically, when you see it like on the news, the way that's calculated today is using something called a consumer price index. So this measures average change over time in consumers' cost of living. So who's heard of a consumer price index before? Yeah, most people. Okay, so good that you're familiar with it. Essentially, the way it works is, okay, I could go and look at like the the price of gas, for example, 1 year versus another year. Or I can look at what another particular good, like a television or something like that. So what the consumer price index tries to do is it makes a quote unquote basket of goods. And so these are like a bunch of items, like common household items that people spend money on. And so it sort of averages a lot of those price differences that you see over different time periods to essentially capture your average inflation over time. So what might be a drawback of something like that? Can anyone think of anything? Yeah.
Yeah, it heavily depends on like if you use it as a family or as a person to like get an idea of inflation, heavily depends on what you're actually buying. So you might not get the exact same things, but you might get heavily different amounts than the things that are in this basket of the consumer price index.
Yep.
So I think it's still like good, like it's good to visit and compare inflation across different countries. Get an idea of it, but you, yeah, like your own experience inflation might be higher otherwise than that.
Yep, exactly. So the representation, the representativeness of your consumer price index depends on kind of how closely you follow that sort of basket of goods. Another one would be that what's in the basket itself, right? And so these things could change over time, right? So how many people were spending money on buying like cell phones 20 years ago, right? Or 30 years ago. And so, you know, part of that is part of the issue with a CPI is sort of dealing with some of those dynamics and shifts and what might actually be or what should be within that basket. Yeah.
It's also not spatially
Yeah.
discrete either. So
What people spend money on and yeah. Yeah, right, exactly. Yeah, and we don't spend like the amount of money that Californians spend on heating is going to be really different from what like people in Michigan spend on heating, right? So yeah. So it's not perfect, but it gives, you know, at the end of the day, a fairly decent indication of what's happening. All right. Constant and current dollar. So this is like two ways of displaying sort of currency in different time periods. If you are doing a constant dollar, that includes the effect of inflation, whereas current dollar analysis attempts to adjust for the effect of inflation so that you can be compared on a sort of more equivalent basis. And so typically a current dollar, you're anchored to a particular base year, and then you express other years in terms of those that base year's dollars. So the most common example that people give for constant versus current dollar is gas prices. So, you know, you can talk to your grandpa and they're like, oh, back in the like 70s, you know, price or a gallon of gas only cost me, you know, 80 cents or whatever, right? And so that is true for what they were paying then, but then you had a big difference of inflation, right? And so in 2000, what was this, 2012 dollars, adjusted for inflation, they would have been paying, you know, $2 to $3 a gallon, equivalent of today's dollars, right? All right, any questions about inflation? think this one is maybe the most straightforward. Okay, so interest rates. Similar in concept, and in fact, a lot of the ways that you'd essentially like calculate these rates or use the rates are like the exact same equations, right? Because the way these are described as these like annual change rates, usually. So again, this is when a lender loans money to a borrower. So they have some incentive essentially to, charge money for that service. So interest to borrow money. So typically expressed as a percentage, and it's the proportion of the amount loaned, right? And so there's lots of different interest rates that we think about. So you may have heard like, oh, the Fed is changing its interest rates. So this is essentially a directive of our government to the central bank to set a specific interest rate. And that essentially influences a lot of the interest rates that you see in other sort of contexts, right? And so depending on the interest rates can vary depending on a whole bunch of different factors, right? So, all right, so does anyone bank with a major bank? Right, you guys all have, I'm sure, have bank accounts, and so if you're putting money in like in a savings account, right, you have pretty bad interest rates. Does anyone know what those are these days for like major banks? Yeah, right. So really, really small. But if you were to, for example, go buy a house, the interest rates that you would be subject to, right, are really different from what you're getting from like a bank's interest rate, right? The interest rate to buy a car would differ from the interest rates that you would get in buying a house, right? And so depending on the size of the loan, your interest rates can vary, right? Depending on the term to maturity of the investment. So you can imagine that my interest rate for saying, oh, give me back my loan tomorrow versus in 15 years, right? That could be really different. Perceived risk of the transaction. So if you got two people and one person is really reliable and will always pay on time versus someone who doesn't pay back money, you might have a different interest rates for those two different types of people, right? Okay, so interest on principal, so the amount that you would actually be sort of paying back can be calculated in a fairly straightforward manner. Compound interest, most powerful force in the world. So this is the equation that you could use to calculate what like a compounding interest would be. So we'll do a quick public service announcement, right? If you want to retire, you should be investing into retirement as early as possible to take advantage of compounding interest, right? So this is a plot that shows if you're making sort of regular annuities into a retirement fund, how much you would retire at the age of 65, depending on when you start investing. And so if you make more off of the first 5 years, right? That's a quantity equal to like $200,000. you make more in the first 5 years than the last 25 years because of compounding interest. So start early. Okay. Any questions about interest rates or confusions? Yes.
Is the R-value of the equation just for inflation already? Is it real or not? You already get the inflation out, or do you do it later?
Yeah. So technically speaking, like in these types of things, it's not really accounting for inflation. You could by sort of factoring them together, having like a combined rate, but it's not too common to do that in analyses. Yeah. You could always do this first and then adjust for inflation afterwards. Okay. So the last one, and this one tends to be kind of the most confusing. So discount rates is the preference between value of consumption today and consumption in the future. Okay, so let's walk through this first. So present value or present worth analysis, right? So discount rates often referred to, it's essentially like the time value of money. These are related to some of these concepts, but they are not the same. Discount rates are not inflation rates. They're also not interest rates, but they are influenced by inflation and interest. So present value of a quantity of money C spent in some future year N can be given like this. I'm going to come back to this really quick. I want to make sure we have a good sort of grounding for what this is. So we're going to do a little sort of thought experiment here. Okay, so I need a volunteer. All right, you volunteered. I'm going to give you some money. Okay, I'm going to give you $1,000. I'm going to give you $1,000 today, or $1,000 1 year from now. Would you rather have that money today, or would you rather have it 1 year from now? Today? Why? Why not be safe and get in the year? Okay, so you're thinking about decrease in purchase price. So if I were so let's say you're concerned about inflation. So if I were to offer you money, then I should at least account for inflation, right? So I'm going to give you $1,000 today, or $1,005 next year. What are you going to take? Still today? Because you could just stick it in a bank and make more money, right? Even if you didn't want to do anything with it, you stick it in a bank, your interest would be enough to make more than that. Maybe oh no, maybe not. Well, if you banked on like Ally or something, which gives like 3%, I feel like I'm a shill. Okay, $1,000 today versus $1,050 next year. 1,100. Okay, great. So okay, so who else here who would not take that deal? 1,100. 1,150. 1,200. 1,250. 1,300. You do 1,300. Cool. Okay. So, all right. So.
You got 30%.
Bitcoin, baby.
Okay. So you can see different people have different discount rates, right? So let me ask you, hypothetically speaking, so you have a fairly aggressive discount rate. So what is your reasoning for why you would take like 1,300 but not 1,200. Just qualitatively, you don't
I
need
just
to.
take it purely as a way the risk of
Mhm.
like skip town. Never pay that.
Sure,
You have
right.
to weigh up
These are,
cost analysis of like,
yeah.
$1,000 now. Chance, it's not a guarantee.
Yeah, exactly. And then a lot of times what goes into that calculus is you think, hey, I think that if I took $1,000 today, like I could probably make more than 30%, or I could probably make up to 30% back, maybe I'll invest it or something, right? And so that's the kind of calculus, all of these things play into a personal decision, right? And so, okay, so then we'll calculate these, right? So we had $1,000 today. So that's going to be equal to 1,100 over 1 plus R, and then we had $1,000 is equal to 1,300 1 plus R. Okay, so we'll have R1 and R2, and so this is like an easy, sort of straightforward way that we've sort of immediately demonstrated a way to elicit different people's discount rates. And I can just calculate that R in both of these cases, right? And so, you would have a 10% discount rate and you would have a 30% discount rate in this case. And again, like this can be specific to not only to the individual, but to specific circumstances as well, right? And so, yeah, and so these things, there's a tremendous amount of variability related to discount rates. Yeah.
I think in the second way, you multiply the R2 by 0.5, 50% chance that you skip.
Yeah, that's right.
Then you get the real
Yeah.
R with the
So there's like there's like risk associated with these particular things. Yeah. So he thinks that I'm not particularly trustworthy, which drives the discount rate up, right?
We bike a lot.
It's okay. I'm difficult to offend. Okay. So when you think about doing analyses for calculating like, oh, should a corporation make an investment, right? You should account for discount rates, because I can tell you certainly, companies and individuals do, right? And so to give like a sort of high level spectrum of typical sort of discount rates, businesses often use slightly higher discount rates, so 10 to 15%. Regulated utilities, as an example, 6%. Most like private individuals, if you were to do these type of like experiments in like a more realistic setting type of thing, typically you're eliciting like 5 to 10% for individuals, and investments in developing countries, 15 to 25%. Generally, the higher the risk, the higher the discount rate, right? So if he thinks that I'm skipping town, higher risk, it's going to have a corresponding sort of higher discount rate. And also, one of the big things driving differences between like a business and an individual, right? The difference between those discount rates was that concept I was mentioning earlier. Like a business or a company may have better means to essentially take advantage of capital, and so they think they can make more money off of whatever that sort of initial investment is, which is another reason why you might have like a higher sort of discount rate. Okay. So yeah, let's take a look at this. So future value method is a way of thinking about these things. So you can buy a painting for $10,000, and it will be guaranteed to be worth $11,000 in 1 year from the day that you buy the painting. So you need to consider the opportunity costs associated with, you know, losing that $10,000 for a year, right? And so you can make a table or diagram of streams of benefits and costs over time. I'll do this with another example in just a moment. But here we have a couple different analysis options to do. So if I had access to, let's say, a bank that gave me 8% annual interest, well, one of the opportunity costs associated with this painting, with buying the painting, is that I couldn't take that money and put it into earn simple interest, right? And so in this case, let's take that $10,000. Let's put it into a bank to earn this, and 1 year later, I'll have $10,800, right? And so would I buy the painting if these were my only two choices? I see some people shaking their head, some people nodding. So okay, so this is why it's, you want to be able to sort of explicitly think about this and do these types of analyses, right? So in this case, option one, I get 8% annual, and then I make $800, so I get $10,800. But that's less than the $11,000 that I'm guaranteed to get for buying the painting. So, you know, if we're just thinking sort of financially, the sort of better decision would actually be to buy the painting, right? Does anyone? Yes. So, okay, so remember that the scope is just what's here, okay? So you're saying you could make more interest, right? But then I can sell the painting guaranteed for 11,000, stick it in a bank, and I have a $200 head start in year 2, right? Did I see someone else maybe raising their hand? No? Yes.
Yeah, I thought there were costs associated with selling the painting. So like maybe you have to sell it monthly.
Nope.
Yeah, no,
Guaranteed. We're trying to make this as simple as possible. So from a decision maker perspective, if we're thinking just about the like economic perspective, you always choose the option that maximizes your net benefit, okay? Yeah, and so we're using that same rule with values adjusted for time value of money, and you want to choose the option that gives the highest value. So in this case, you buy the painting. Yeah, so it's called future value when you compound current value to the future. So you can actually do this problem in reverse. Okay, so how much money would you need to invest in savings to get $11,000 in 1 year? And so we can use our equation here, present value, future value divided by 1 plus your rate. And so if you solve for future value, then you have your $10,000. Let me use a different color. You have your $10,000 as your present value, so that's your PV, and then your future value is this thing here. So if if I were to start with my future value of $11,000 at an 8% interest rate, then what I would have needed to start off with to make that much money would be 10,185. Okay, and so since that's bigger, then you should buy the painting because you have a lower investment cost than what would be required to make that money back. So they're both equivalent analyses, but you can approach it from sort of either side. Any questions or confusion here? Yeah.
Put an economic value and the risk associated with painting and stolen inventory analysis. Is there a method to put?
Yeah. So okay. So what I'll say, we are actually going to cover risk in decision making, but that comes a little bit later in like 1 or 2 lectures. So keep that in mind. And yes, there's actually very good ways of integrating things like risk into your analysis. But for now, we're just like straightforward. There's no caveats or anything with the assumptions here. Yeah. Essentially, the way to think about it is that I know, okay, this one is mainly dealing with interest rates, but when we think about this quantity here as a discount rate, that has already incorporated the like risk values. So we've kind of brushed past that point already and saying we've taken that into account. Okay, the last way that you can do this is known as the net present value method. So current investment of $10,000 for painting represented as negative $10,000, right? Because you, anytime you spend money, it's the negative, and anytime you get money, it's positive. So that's one way to think about this. And again, I'll show kind of a visual. Actually, we'll just do it for this one. We'll go ahead and do a little visual example. So this is one way that I like to kind of think about this conceptually. Over the lifetime of your sort of calculation that we're thinking about. In this case, there's just 2 years, right? It's year 0 and year 1. So that's your start. So we're going to have something like this. We'll have 2 dots. This will be year 0. This will be year 1. So in year 0, you have negative $10,000. And then in year 1, you have positive $11,000. But you have to apply all of your the changes in time-based effects on every consecutive year. And so in this case, it'll be 11,000 divided by 1 plus 0.08. Okay, and so this equals your 10,185. And so then you just add up all of the things in every dot and you end up with 185. And so because your NPV is positive, then this particular investment decision kind of makes sense and that you would want to do that, right? And so this is a easy way of doing a comparison against different sort of alternatives or different sort of investments. Any questions? In general terms, present value, future value, and then net present value. Okay, so that is the sort of high level concept of how you would integrate time value of money into some of these things. So this can be, right, essentially your discount rate to figure out, how much money, if you know how much money you're making in the future, how much it should be worth today, or if you have some amount of money today, how much it would be worth in the future, given some kind of discount rate. And then for that investment decision, you can calculate your benefits versus costs as they flow through time to figure out if it's positive or negative, as a way of determining whether or not you should make that investment, or to compare different investment decisions. So let's talk a little bit more specifically about a common, question now, just stretching. All right, cool. Common ways that this has been applied in sort of energy systems and thinking about energy investments. So this is a way of doing an MPV of total system costs. Let's actually let's dive into a specific example. Actually, I need to show one more thing before we get there, or a couple more things before we do that. But we're going to dive into an example to see how to break this down and conceptually go back to what I was just showing with the NPV at dot graph, and hopefully this will make more sense. It's much more important for you to understand the concept of what's going on here rather than just memorizing this equation. But essentially what's happening is you have capital costs, and then you have a bunch of variable costs up here, right? So these are costs that are happening sort of per year, and then all of those costs are getting discounted. So that is essentially the NPV equation with all of your future values up there that are getting discounted, and then you have an initial one over here. And in fact, if you're to think about this carefully, you could actually have a t over here divided by 1 plus r over t. If all of the capital cost is being made as an upfront investment, so you would only have this value at t equals 0, in which case 1 plus r to the 0 would just be 1. And so that's why it's not under that summation equation. Yeah.
Shouldn't the fixed earner fuel and variable earner be more than at the end of life present value of future value? Should be breaking down into annual stream of payments?
It is, right? Because you have a t subscript. So this is in year 1, in year 2, in year 3. Yeah.
The lifetime of the
Yeah. But you can treat it as an annuity if the stream is constant, if all of those numbers are the same every year. Yeah. Yes.
If you do the discount rate properly, you can make it an annuity even if the stream.
Yes, you could. But then, yes, no. If what you're, yes, yeah, you can. If that's what you're trying to get at, and is the annuity. Yeah. So I'm thinking of it in a context of doing an annuity to simplify the equation. You're thinking of it in a context of if I want to figure out what the annuity should be.
Well, I'm saying even for this, you don't necessarily need to have varying O&M. If you know the varying O&M is going to be for the life, it might be different per year. You can still do the annuity and make it the same for year unless there's a reinvestment decision that you have to make.
Yeah, but you have, yes, except that to do that, you're basically doing this calculation anyways. Yeah.
Well, if you're only doing varying O&M.
Yeah. Yes. O&M is, sorry. So I'm thinking about this in terms of a power plant. So fixed O&M is the fixed operations and maintenance cost. So that means like every year I have to like clean this thing. Every like 6 months I have to just do like a cleaning or something. You also have fuel costs to like run the plant, and then you have variable O&M, which is like it's like, oh, depending on how much I use it, I have actual different amounts of operations and maintenance. Yeah.
Do I have to consider like transmission and distribution costs?
It depends on what you're exactly what you're measuring. Yeah.
It's like the fence line.
Okay. Couple quick concepts. Internal rate of return. So this is for an investment, sets the net present value of a revenue stream to 0. So this would be essentially, this would be what your discount rate would essentially need to be in order to like break even. So it allows for comparison across a wide variety of investment activities. The higher your internal rate of return is, the more profitable the project, or the less risky the project. Payback period. This is the amount of time during which your initial capital expenditure is essentially recouped. Okay. A simple payback period is the difference in your total costs, all of the costs, divided by the difference in annual sort of operating costs. But then with a discounted payback period, you're looking at discounted, you're looking at all of your sort of costs discounted. Payback periods, acceptable payback periods for investments can vary depending on the individual or company, but typical ones you'll usually find like 12 months to 3 years, and that'll be, you know, equivalent to some sort of like relatively high discount rate. Yeah.
How closely would the discount rate be proxied by the interest rate on safe assets? So let's say a bank deposit. So can you use, let's say in a problem, that if the safest deposit rate out there, like, I don't know, 0.2, something like that, can you use that as a proxy for the discount rate? Because often investors think, okay, what is the next best option I have? That it's the safest asset I can put my money in. And that's how they calculate the NPV. So can you use that as a proxy? Is that a one-for-one proxy?
Yeah.
Wall Street's gonna kill you if you're only making 1% on your money.
Yeah.
So in problems, then what do you use? If you're using it, putting a discount, do we given the discount rate? Or do we have to?
Oftentimes you'll be given a discount rate, but again, it's related to your ability to make money, right? And so, so setting the discount rate to like 1%, maybe that makes sense for like a very conservative individual, but for a company, they're going to be like, no, like I can definitely make more than 1%. Like even if I were to take a really safe option, maybe they think they can make like 10%,
Maybe
right?
Treasury bonds, is that a discount rate that is often used? I've heard that come up, as you know, that the bond is like the next best safe option.
Yeah, so bonds can be an option to think about. Yeah, but like it's not like the decision-making process. The discount rate is essentially trying to emulate the decision-making process for a decision maker, right? And so, you know, that is an important, like alternative ways of making money is an important factor that goes into it, but it's not like oh, okay, I'm going to look at this investment and I'm going to go into my like table and look up like discount rates that are, you know, full. It's a process that is meant to capture all of that decision making into essentially a rate that can represent the types of decisions that are being made by that person or company. Yeah. Okay. Annuities. So this is what we were just talking about. So consider the present value of getting the same amount of money for many years. So in your present value in year 1, you get A. In year 2, you get A. In year 3, you get A. And then this would be the math to calculate the present value of those stream of payments. And so you can actually simplify this so that instead of putting this into your calculator, you can just put this equation. And so this would describe your present value of some annuity that's being paid over many years, n years, and you just plug in this equation and that will tell you the present value of those annuities. So this is a simplification a lot of times for problems where all of your A's are essentially the same.
About discounted,
Sorry, it's
really often fixed annuity and operating costs. At first it's brand new, doesn't cost a lot. By year 10, it's throwing at an annual 2% fixed cost. Is that what kind of?
Yeah, so in this particular example, that's talking about like just a steady stream of payments. If you had like ABCD or differing sets of payments, you could actually transform it into an annuity, right, by essentially doing that equation, getting into a present value, and then dividing it across all of the years. And so then essentially it would be this amount of money that's equivalent every year that would cover all of the stuff, all of the variation that's happening year to year. And so that's what he was talking about earlier. So that would not be like a shortcut. That would be if you were interested in actually developing an annuity to figure out what that equal payment should be. How would you do that? Right. This one is more of like simplifying that equation into this. A common concept in energy systems is thinking about the levelized cost of energy or the levelized cost of electricity. And so essentially what you're doing there is you are doing the present value, right? This is that equation that we had before of your of like your maintenance and varying costs, and then you divide it by the total amount of energy. Okay, so let's kind of demystify this, right? So what we had before in that NPV equation, right? Let's say that is telling you that is telling you how much it costs to build a power plant, right? And then it includes all of these like downstream costs of the fuel, of the operations and maintenance, and so on and so forth. So let's say it costs like $10 billion in present day dollars to build the plant and to operate it for the next 30 years. I can divide that by the amount of energy that power plant produces over the next 30 years and get $1 per kilowatt hour, right? And so that's an easy way to sort of get a sense of the cost to produce one sort of unit of electricity. And so that immediately lets me do comparisons, right, of like a power plant, if I wanted to build power plant 1 versus power plant 2 versus like a solar farm, you could do this type of equation to do that comparison. Let me go to this example first. Okay, so let's take a look at this example. So we've got a rooftop solar PV system, and we have a coal power plant. So my question to you would be, should I go around and build a whole bunch of solar PV systems, or should I build a coal plant? Right, these are vastly different in size and use case, but we're gonna just sort of simplify this for now and say, so we have all these attributes of the system, right? We know the size of it, we know the capital cost, we know the maintenance, fuel cost, how much it's gonna produce in 1 year, how long it's gonna last, and then we'll have like a discount rate. Okay, and then we have this power plant, 600 megawatts, capital costs, maintenance, fuel costs, so on and so forth. Okay, so then which one should I build from an economic financial perspective? Yeah, sure, yeah, we calculate it, yes, exactly. So, okay, so let's do that. So starting conceptually, let's do solar first. So solar, and really quickly, just as a refresher, right? So capital cost 100,000. The only annual costs are $3,000 of maintenance per year. Okay. Yes. But let's do the sort of dot diagram first. So year 0, year 1, year 2, year 3, and so on and so forth. So in year 1, we have negative 100,000. And then in each year following that, we have minus 3,000. Okay, all the way dot 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 to year, what did I say? 25, year 25, negative 3,000. Okay. So my LCOE equation. So I don't even need to think about the equation. I can just like look at this chart that I've made, right? I can say it's $100,000 plus $3,000 divided by 1 plus, my discount rate is 15%, so 0.15, and that's to first power, plus $3,000 divided by 1 plus 0.15 squared, and so on and so forth, all the way to my last one, 25. It's 25. So yeah, this part can be confusing a little bit, but think about if I bought a solar, if I bought a solar panel today and it lasts for 25 years, then it would be 25 years later, but then at the beginning of year 1, which I'm denoting as year 0, is like when I actually like pay the money for it, right? So yeah, this would go all the way out to 25. Okay, and then I can actually simplify this based on the annuity equation, right? And so this would be equal to 100,000 plus that annuity equation thing, which is 3,000, 1 minus 1.15 to the negative 25 over 0.15. Oh, and I should divide this whole thing by 182.5 megawatt hours per year times 25 years. That's the dividing by the energy part of things. So that would be this whole quantity divided by, that would be 4562.5 megawatt hours. And so this ends up being equal to 26.17 per megawatt hour. Yeah. Actually, I should change this example because I think the coal plant is better, but okay, so this is right, the concept in which I would apply this thing. And so this, I mean, this, what I wrote here is that equation, but hopefully you guys can understand how I've like translated it from this like dot diagram. It's not, it really is not that complicated. You just take each stream and then for every year you divide it by this to the power of that year. Yeah.
Where do you have escalation factor? These payments are rising at say constant rate. Where do you plug in the escalation factor just in the discount rate below, or do you also make sure that the O&M payments, the fixed ones, are also rising at that rate?
If it's like, if you're saying if the payments are going up over time, all you would do is you just change these numbers here, right?
There's no way
Instead
you
of
could
3,000.
Are
multiply,
you asking if you're trying to increase by like?
yeah, escalating when you.
Yes.
Yes.
If you do interest rate, you have to do your rate, like 15%. You have to
Yeah, so there's the way that you could do it. So
1,000 with 1 plus the escalation rate times 2 is that way? Or do you might do you subtract it from the discount rate as well?
yes, so you're saying 1 plus, let's call this I instead of R to the T divided by 1 plus my discount rate to the T, which is equivalent to what you were just saying, 3,000 divided by 1 plus R minus I to the T. Yeah, so they would be the same. Yeah.
Now, if you want to change in interest rate.
Yeah, but so yeah, so there are all these little things that we can talk about, like including the interest rate or varying these things, but like don't get like, this is just a simplification to represent that, but don't get hung up on this. You can always go back to here and just change that number, right? According to like interest or something. And so that can be your fallback instead of trying to like memorize a particular equation. Okay, is any other questions on this? Okay, so we can do this same sort of calculation, right, for coal, and I can do in year 0, I can have this dot, and instead this could be $2 billion instead of 100,000, and then in year 1, and so on and so forth. It would be, I can't even read my notes, about $42 million a year in operations, operations and maintenance costs and fuel costs, right? And you can put that into your LCOE equation. So 2 billion plus, what do I have this as something different? oh, sorry, this is half. So this should be 85 million. So it'd be 2 billion plus my 85 million times 1 minus 1.15 to the negative 25. It's 40? What am I, why did I? Oh, sorry. Yeah. Okay. Yes, sorry. Divided by 0.15, and then this whole thing gets divided by 3153600 megawatt hours times 40 years. And this whole thing will eventually translate to 20.34 per megawatt hour. Okay, I really should change this. Yeah, let's throw in a carbon tax and we'll add like extra, $50 million to the annual payments. Yeah. I should definitely change that. But anyways, so that is essentially how you would do these calculations, right? And now, hopefully it's clear to everyone how I can leverage these tools to do these sorts of comparisons, right? And so now you can answer this question, looking at with all this information, we know how to approach this and how to do like a NPV comparison to see which one's cheaper to provide electricity. Okay. So what do the numbers actually look like? So these are levelized costs of energy. So people have done this kind of comparison to real world projects to look at these things. Oh, yeah, sure. You want to look at the example? Yeah. My drawings? Maybe. Okay, yes. We can do it. Yeah. So again, this is your simplification of your annuity equation. We have the capital cost there, and then we're dividing it by the energy that it's producing over its lifetime. Actually, this quantity here, some people will discount that. It's a different way of doing the LCOE, but yeah.
The plan, so 60% like capacity factor. You have to like include that in the energy production.
I didn't.
You just gave
Did I?
going to produce this much at 6%.
Yeah. So, but good point. So, if this was the, if I did not include this number, but you have the capacity number, you can use the capacity factor to determine what that would be. So that calculation would be 600 megawatts times 8,760 hours in a year times 0.1 or 0.6 as the capacity factor. Okay. Okay, did you see? Yeah. I'll change the numbers next year. Okay. So let me jump back over here. So these are the actual numbers that people have done this analysis on, looking at real projects. Yeah.
That was just the cost across to produce, not how much money they make from it and they can charge it.
Yep, exactly. It is more expensive. See, this is rooftop residential, here's coal, but then utility scale is actually cheaper these days than coal. But yeah, you get a sense of essentially the calculation of the LCOE across different technologies that gives you a easy basis of comparison between these different electricity producers. Yeah.
Are those in ranges with different assumptions or different studies?
Ye-
Different methodologies require the range?
Yeah, ranges because different projects in different places, and like these things will produce like different amounts of electricity as well, right? So you know, yeah, like not everything costs the same. Not all of these technologies have the same capacity factors. Yeah, so yeah, yeah,
So this is typical for a project, so for a plant that's weighted
yeah.
20 megawatts, I think that's listed in the footnotes there.
So you can look at some of the like assumptions here.
How to the turn square and
Oh, what are the diamonds? Let's see, what's 5 say? Represents the midpoint of the marginal cost of operating fully depreciated facilities, including decommissioning.
I think that's just special cases. It's like if the asset of the coal plant like entirely paid off, every marginal like megawatt.
Yeah.
Pure profit, so that's like LCOE after that. I think if coal plant where you paid it all off and you're just running it and you basically just like.
I would I think they're just discounting the retrofitting of the plants and all those numbers in the.
I think those are the special cases because if you see number 2, which is the diamond blue, the wind case, it says that this is like the midpoint of the offshore wind cost. So
There, it looks, so it actually looks like they're representing different things. I think, these all have little parentheses that kind of tell you what's going on. These 3 points, I think, is what you were saying, which is after the like assumed lifetime of the plant and it's still operating, you're like what is it? Your free money. It's like you're playing with house money essentially. And so
You're still using it.
Yeah.
It's not including the money mentioned in administrative cost of getting the permits to keep it working after. Like,
so the longer you can think of, one way to think about it is like you're operating it for longer and longer periods of time. And so that lets you get bigger benefits out of it. Because the like proportion now of money from the capital that's getting like amortized over this like longer period of time is
yes.
better
Isn't there,
ratio.
especially with nuclear, costs related to that extra time?
There can be, but it would still be better than like building a new nuclear plant, right? I think that's essentially what's happening here.
like the capital cost to build a new plant is like $10 billion, and you run that for 30 years, whatever, and then that's permanent after 10 years, could be $500 million. Right?
Yeah.
So then it's still producing the same amount of electricity, so it's like the LCOE increases by.
So actually, it's a good point. You know, we're looking at these ranges and the things that kind of go into them, and there are these like particular diamond examples that are essentially discussing like specific conditions that are allowing you to get these values that look really different from you know the rest of what you're seeing in the bar, and that's important. So as it relates to LCOE, this is not like a perfect metric. And so things like that can derive, can be a source of common criticism of this type of approach, right? It doesn't, so one of the things that LCOE doesn't do, right? You're just dividing by all of the electricity produced, right? But the value of electricity produced in at 3 o'clock in California is actually different from the electricity being produced at 9 p.m. In California, right? And so the value of that electricity varies over the course of the day and over the course of the lifetime of this of whatever asset that you're talking about. And so that is not captured in the LCOE. Yeah.
Do you not capture within the capacity factor number? Do you not count the capacity factor that's more reflective of the plant's actual output?
But it's not just the capacity factor, right? It's the timing of when you're providing the electricity.
So when you're providing if you take that as the total output, at any time of the day, you take it, let's say, for 1 year. And then you count with the capacity factor as to what portion of the total nameplate was produced, and that then reflects what the less production at 3 a.m.
No.
That you multiply it with.
No, because capacity factor wouldn't capture this either. Capacity factor just tells you essentially when the plant or power producer is like making electricity, or how often it's producing electricity. It doesn't tell you if when it's producing electricity, it's more valuable. So to give you an example of this, I could be running a natural gas plant at 50% capacity factor. If you have 2 natural gas plants and they're both running at 50%, but this one's selling its electricity at a time that's more valuable. Yes,
Okay.
yeah. The value of the electricity is different.
Saying it only reflects supply and not demand.
Yeah, but they're intertwined, right? Like, yeah. So
We're talking about the cost, not the prices.
Why would you get price metric for a levelized cost calculation? Like, we just want to know how much.
Well,
of
because then
the,
you're doing like trying to do like forward pricing on markets for a plant that like solar that can last for 30 years.
let me so conceptually, let me give you an example of what this means. Okay. Let's say you have a solar plant and a wind farm that look exactly the same. They operate exactly the same. The profiles look the same. The capacity factors are the same, except solar produces during the day and wind produces at night. Okay. So if I do a LCOE calculation, they will be exactly the same, right? Because the attributes are identical. But let's say electricity is worth more at nighttime. Let's say it's like harder to get electricity at night than it is during the day, because let's say you already have a lot of solar. The LCOE doesn't have the ability to reflect the fact that latter, though the wind one is more valuable. That's all that we're saying. So in coming up with this like way to do an apples to apples comparison, right? You're making certain types of assumptions and simplifying things in such a way that some types of values are kind of lost. Yeah, and so that's like one of the most common criticisms, and that's related to all 3 of these points here. Yeah, LCOE can't replace a lot of the more accurate like economic comparisons that look at a whole bunch of other sort of factors. And so, we're not going to get into this. It's just to say that like, have a good idea of like what you're actually trying to represent with doing this LCOE calculation. Okay, last concept that we're going to talk about today. So we're going to dig a little bit deeper into the concept of discount rates. So we know this, right? Self-interested individuals and companies often prefer money now rather than in the future. But let's think about this from a different perspective. Let's think about this from a societal perspective, and what it means to have a discount rate as a society. Because if I were to ask you as an individual, all right, $1 today or 10 quadrillion Googleplex $1 billion in 1,000 years. Yeah, right. And so that is like one of the fundamental difficulties of thinking about things that affect future generations, right? And so like fundamentally the issue of climate change affecting our children, our grandchildren, even if you have like a 5% discount rate, a fairly low discount rate, a 4% discount rate, like the value of $100, $1,000, $10,000 today, you know, 50, 60, 70 years into the future, like rapidly diminishes because of the sort of exponential nature of how discount rates work. So when we think about welfare of future generations, people have started a sort of discourse over the last, you know, couple of decades when climate change has been coming to the forefront of like a sort of different concept of like extremely low discount rates, so that public investments, like money that the government is spending, when you do economic analyses, that you can actually make rational decisions to invest like far out into the future. So these are known typically as hyperbolic discount rates. So you're talking about discount rates like 3%, 2%, 1%, even 0%, right? So people talk about this and think about how to value this so that we can essentially invest in sort of future generations. And it's a controversial, you know, topic. You know, whether you're doing research, whether you're practically doing real world investments, dealing with time preferences in these intergenerational scales is really, really different. And so all of these things that we think about as it relates to our individual or like a company's discount rate for like incorporating inflation, thinking about interest rates, and all of those things that go into our decision making, like thinking about risk and all of those factors that we've talked about today, you kind of have to think of it differently for thinking about discount rates in the future, because as soon as you say, oh, I want to incorporate an interest rate into my discount rate for thinking about my future generation, your value for that future money, again, just gets wiped out very quickly. So yeah, intergenerational time preferences are like fundamentally discount rates that incorporate a different set of values than the ones we're thinking about when we make these individual financial decisions.
So I'm sorry, so,
Yes.
so a zero discount rate, 2 steps, sorry.
Nothing to be sorry about.
Rate, and means that we are assuming that the investment will not generate any money, so future generations can benefit from it without paying back over years.
I mean, that is an example of an application of that type of rate, but really it means that we should think about the value of money today and in the future as essentially the same. That's what a 0% discount rate would be.
Won't gain value over time.
Exactly. So an example of this would be if you were to make like an investment decision in a project that doesn't pay back for 50 or 60 or 70 years, like normally as a company, you would be like, no, that's absolutely crazy, because like I'll be dead by the time that happens. You know, my board of advisors is going to say no, because we're not making any money for such a long period of time, right? But then if you don't discount, basically you're saying, well, it's okay that I'm, you know, pay getting paid back many, many decades in the future, that is the same to me as getting paid back tomorrow, essentially.
So providing a benefit for those situations.
Yes. So you can imagine that that calculus and that decision making, like, is no longer about your traditional like profit making, right? From a financial.
This is the exact opposite of capitalism. How do we
No,
stop
this
it?
is no. So actually, this is an attempt to. This is actually an attempt to make these kinds of investments in the framework of capitalism, right? This allows you to do future investments and calculate out like a positive NPV. So, okay, maybe it's like slightly anti-capitalism, but like you're operating in the type of like calculus and decision making.
Good for all that makes money for.
Yeah,
Yeah, I mean, I'm totally for it.
Yeah.
Just how do you-
it's a challenge, right? And these are the kind of discussions that we now have in like policy making for making investment decisions. I mean, like a lot of times this like companies aren't doing these types of things. I'm talking about like government decision making processes are following these like hyperbolic discount rates.
You know, if everyone has to do this.
Oh yeah, absolutely. There's tons of things, right? Like you can actually think of like a lot of regulatory policies that like that are restricting like or like promoting climate change mitigation, that like the basis of the like economic decision making is fundamentally based off of super low discount rates. A lot of decisions are driven by the work that folks have done in this space, sort of demonstrating like a different concept of discount rates.
So, you know, any like paper reference for how many policy you did that?
Yeah. I like not off the top of my head, but there's definitely a ton of literature in this area.
Can we benefit for this we to associate dollar value to the social benefits that are coming, so we can have a positive value in the coming years?
Yeah, exactly. So yeah, that's a it's a really nice way of verbalizing essentially what's going on here. So so if you were to consider investment decisions making an impact in the future, if you have things that are adding to climate change, there are damages that are happening 30, 40, 50, 60 years out into the future that get discounted away. Because you make this calculus, you say, yes, I know this harms the environment, the climate, but in this like discount analysis, like those damages get divided by a really big number and go down to zero essentially. And so you can decrease those damages or have future benefits happening way into the future that actually get like incorporated into your NPV.
So this over intertwined, somebody mentioned internalizing this.
Different concepts. So internalizing externalities is thinking about incorporating damages, essentially costs that.
Another equation to this.
Yeah. So if you remember the dot thing that I was doing, internalizing an externality would be like adding an extra cost to the money being paid for like coal or something. Yeah. So it's a different concept. Okay, so yeah, some ways of how you would select social time preferences, and people have talked about this. There's a couple of papers here that that you can look at. Yeah, and what you would consider to determine what the rates would be. Yeah, so fundamentally, this is essentially all these things that we've been talking about, right? So reducing emissions last for centuries, but the mitigation costs of trying to do that are born today. And so that's why you need low discount rates, really low discount rates to do this properly. Okay, so we will end here for today. And homework is due next Monday, right? Monday. So yeah, FYI. Also, oh, sorry, hang on, before anyone leaves, I'm gonna send a poll if people want to do, maybe I'll have like a alternative office hours. So office hours are on Tuesdays, but it sounds like a lot of people can't make it. So I don't know what the best way to ask. Okay, we'll do, well, I'm gonna do a poll for a couple times and then you guys can answer that. And then you know, there's another set of office hours from our TA too. So